Hi guys, this is the EdExcel A-Level Further Maths Paper 3 from the sample papers, and in this video we'll be taking a look at the Further Pure 1 FP1 module. For question number 1, we have to use the Simpson's rule with 6 intervals to estimate the integral from 1 to 4 of the square root of 1 plus x cubed with respect to x. And at this point, I think it would be a good idea to write down the formula for the Simpson's rule. So we have our Simpson's rule formula. The integral of y with respect to x from a to b is approximately equal to h over 3 lots of the first y value plus 4 lots of the odd y values plus 2 lots of the even y values plus yn. And when we come to work out this problem, you'd see what I mean when I say y odd and y even. But first, let's work out what h is. You'd find over here h is equal to the upper limit minus the lower limit. So we have 4 take away 1 over the number of intervals, that would be 6. It turns out h is equal to 0.5. Now, let's create a table of x and y values, and let's evaluate with different values of x the square root of 1 plus x cubed. Okay, so we have our x values. We start off at 1, we want to end up at 4. We're going up in a step of 0.5, so we have 1, 1.5, 2, 2.5, 3, 3.5, and 4. Okay? And then we need to work out our corresponding y values. So, working out our corresponding y values, let's grab our calculator. Here we have 1 plus 1 cubed, that would be the square root of 2. So we have the square root of 2. And then we have 1 plus 1.5 cubed, that would be 4.375. So here we have 4.375 square rooted. And then we have 1 plus 2 cubed, that would be 9, and then the square root of 9, that would be 3. And then we have 1 plus 2.5 cubed, that would be 16.625, and then we square root that. So we have here 16.625 square rooted. And then we have 1 plus 3 cubed square rooted, that would be root 28. And then we have 1 plus 3.5 cubed and then square rooted, so we have the square root of 43.875. Okay, and then we have 1 plus 4 cubed square rooted, so we have the square root of 65. Okay, so now let's actually state these y values. So we have here y0, y1, y2, y3, y4, y5, y6. So when we come to work out the approximation for the integral, we have the integral from 1 to 4 of 1 plus x cubed square rooted with respect to x. That's approximately h over 3, so we have 0.5 over 3 lots of the first y value the square root of 2 plus 4 lots of the odd y values, so we have y1, y3 and y5 added together. So we have here 4.375 square rooted plus the 16.625 square rooted plus the 43.875 square rooted. Okay, and then we have 2 lots of the even y values, so we have y2, which is 3, plus y4, which is the square root of 28. Okay, and then we add on our final y value, y6, so we add on the square root of 65. And we now need to write all this into our calculator. So we have here the square root of 2 plus 4 lots of the square root of 4.375 plus the square root of 16.625 plus the square root of 43.875 and close bracket, and then we have 2 lots of 3 plus the square root of 28 and then close bracket, and then we add on the square root of 65. It turns out we get 77.23 etc, and then we multiply this by 0.5 over 3, so it turns out we get 12.8718 etc. So to 3 significant figures we get 12.9 to 3 significant figures. Okay. Question number 2. Given that k is a constant and that y equals x cubed lots of e to the power of kx, we have to use Leibniz's theorem to show that dny over dxn is equal to this result over here. And I think it would be a good idea to actually state what the theorem is. So here we have stated the actual theorem. If y is equal to uv, where u and v are both functions of x, then dny over dxn is equal to the sum of n choose r dru over dxr multiplied by dn minus rv over dx n minus r from r equals 0 to r equals n. In other words, as one decreases, the other increases. Okay, and then we have the coefficients of the binomial expansion. Okay, so I think it would be a good idea to use different colours. So if we let u equal x cubed and v equal e to the power of kx, let's first of all work out the derivatives of u. So we have du over dx, that's equal to 3x squared, hopefully that's straightforward. D squared u over dx squared, that's equal to 6x. D cubed u over dx cubed, that would be 6. And d4u over dx4, that's equal to 0. And hopefully you'd be able to recognize that the fifth derivative, the sixth derivative, etc. will all equal 0. So let's just write that down. We have the derivatives are all equal to 0 for r being greater than 3. Okay, let's now look at the derivatives of v. Now, the way we approach this, if you consider this formula, what we have done over here is worked out these derivatives over here. So we will start here, then we will go up here, 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 and then continue on. So if you consider, for example, dv over dx, dv over dx, that's equal to k e to the power of kx, d squared v over dx squared, that's equal to k squared e to the power of kx, d cubed v over dx cubed, that's equal to k cubed lots of e to the power of kx. And hopefully you can see where this is going. You should be able to notice that dnv over dxn is equal to kn e to the power of kx. Now, the reason we want to do this is we want to work backwards in some sort of sense from here. So essentially, what we want to do is correspond the terms as necessary. So what we mean by that is this term corresponds to this term. Okay, let's just write that down. dnv over dxn, that's equal to kn e to the power of kx. And then working down, the corresponding term here would be dn minus 1v over dx n minus 1, and that will equal k to the power of n minus 1 e to the power of kx, and that's it. Continuing, we have dn minus 2 over dx n minus 2, that's equal to k to the power of n minus 2 e to the power of kx. And continuing, we have dn minus 3 v over dx n minus 3, that's equal to k n minus 3 e to the power of kx. Continuing, n minus 4 v over dx n minus 4, that's equal to k to the power of n minus 4 e to the power of kx. And this is all important because what we can now do is use the theorem and add the terms together. Don't forget to include the coefficients as well. So what we mean by that is the following. We have dny over dxn, that's equal to u lots of dnv over dxn, and then we have n choose 1 du over dx lots of dn minus 1 v over dx to the power of n minus 1. Then we have n choose 2 d2u over dxn, lots of dn minus 2v over dx n minus 2. And then we add on n choose 3, lots of d cubed u over dx cubed, and then we have d n minus 3v over dx n minus 3, and then we have n choose 4 d4u over dx4, lots of d n minus 4v over dx n minus 4. And then we've got other terms as well which we can add. And all we have to do now is simply substitute in everything we have over here into this formula here. So we've got u, which we said was x cubed. So we have x cubed multiplied by dnv over dxn, which we said was this term here, kn e to the power of kx. And then we have n choose 1. Now n choose 1, that's the same as n over 1 factorial. And then we multiply this by du over dx. We said du over dx was 3x squared. So we have 3x squared. And then we multiply this by this term over here, which we said is k to the power of n minus 1, lots of e to the power of kx. And then we have this next term, n choose 2, that's the same as n lots of n minus 1 over 2 factorial. And then we have d2u over dx, 2, sorry, this should be 2, which we said was 6x. So we multiply this by 6x, and then we have this term over here, which is over here, that's k n minus 2 e to the power of kx. Okay, and if we continue working the other terms out, we have now n choose 3, which is the same as n lots of n minus 1 lots of n minus 2 over 3 factorial multiplied by we're going to multiply this by d cubed u, so that's 6, and then we multiply this by k to the power of n minus 3 e to the power of kx, and then finally we have n choose 4. So we have n choose 4, which is the same as n lots of n minus 1 lots of n minus 2 lots of n minus 3 over 4 factorial, and then we multiply this by this fourth derivative, which is 0, and then we multiply this by k to the power of n minus 4 e to the power of kx. And we can carry on, but there's no point because all this term will disappear and every term after it will disappear because of this statement here, that r being greater than 3, the derivatives will all equal 0. So hopefully that makes sense. So the remaining terms disappear. Let's just write that down. So note the remaining terms disappear. Okay, so now let's tidy all this up a bit. For the first term, we've got x cubed lots of k to the power of n lots of e to the power of kx. For the next term, we've got n over 1 factorial, which is n, and then we multiply it by this over here. So we have 3n x squared multiplied by k to the power of n minus 1 e to the power of kx. And then we have this term over here, so we have 6 over 2 factorial, which is 3. So we have 3n lots of n minus 1 lots of x lots of k to the power of n minus 2 e to the power of kx. And finally, we have this term over here, n lots of n minus 1 lots of n minus 2. And then we have 6 over 3 factorial, which is simply 1. And then we have this multiplied by k to the power of n minus 3 e to the power of kx. And we don't need to continue because, as we said before, the remaining terms disappear. And we want to show that all this result is the same as the result we have here, which it is. And I'll show you why that's the case. So first of all, in conclusion, dny over dxn, what we can do first of all, if you look at what the answer is, they have factorized out a k to the power of n minus 3 e to the power of kx. So let's do the same. Let's factorize out the k to the power of n minus 3 e to the power of kx. And then we have the terms inside the bracket, which we can quite easily work out. Well, this term over here multiplied by k cubed and then x cubed will give this first term here. The reason being, when we come to add the powers for the k terms, k to the power of n minus 3 plus 3 is the same as k to the power of n. And then for the next term over here, we have k to the we have 3k, we have 3 multiplied by n, and then in terms of k, we have k squared and then x squared. So what you'll notice over here, k to the power of n minus 3 plus 2 is the same as k to the power of n minus 1. And then obviously we still have the other terms outside. And then we have the 3nx squared inside the bracket. And then here we have 3n lots of n minus 1 lots of kx. The reason for that is k to the power of 1 plus n minus 3 is the same as k to the power of n minus 2, and then the rest of the terms are shown here and here. And then finally we have simply n lots of n minus 1 lots of n minus 2, which is our final term. So hence we have shown the result. Okay? Question number 3. A vibrating spring fixed at one end has an external force acting on it such that the center of the spring moves in a straight line. At time t seconds where t is greater or equal to 0, the displacement of the centric of the spring from a fixed point O is x micrometers. the displacement of C from O is modelled by the differential equation t squared lots of d squared x over dt squared minus 2t lots of dx over dt plus 2 plus t squared lots of x equals t to the 4. For part A, we have to show that the transformation x equals tv transforms this equation into this equation here, d squared v over dt squared plus v equals t. And for us to do this question, what we would have to do is differentiate this over here, and then with that we can differentiate that again and then substitute into here. We want to replace the x's essentially with v's. So for part A, so far we have x equals tv. Okay, let's just write this down. X equals t times by v. And now if we differentiate this, okay, so let's differentiate this. We have dx over dt using the product rule. We have u times by v dash, so we have t times by dv over dt plus v times by u dash, which is 1, and tidying this up a bit, we end up with v plus t times by dv over dt. Okay, and if we find the second derivative, and the reason I want to do that is I want to replace dx over dt and d squared x over dt squared into something involving v's. So if we find out the second derivative, so d squared x over dt squared, differentiating v, we end up with dv over dt. Okay, and then again using the product rule here, we have t times by d squared v over dt squared, so we have d squared v over dt squared plus dv over dt times by 1. Okay, so I'll just use the product rule again over here. And if we tidy this up, dv over dt plus dv over dt, that's 2 dv over dt. So we have 2 dv over dt plus t lots of d squared v over dt squared. Okay, and if I call this 1 and if I call this 2, we can now substitute in 1 and 2 into I over here, and hopefully that will eliminate all the d squared x over dt squared, the dx of dt, and the x. We'll end up with something involving v's and t's instead. So let's just write this down. We will now substitute in 1 and 2 into I. And if we do that, well, we have t squared lots of this thing over here. So we have t squared lots of 2 dv over dt plus t lots of d squared v over dt squared. Okay, then we have minus 2t times by dx over dt, so we have minus 2t, lots of this over here, v plus t dv over dt. Okay, and then we have 2 plus t squared, lots of x, and remember x was tv, and this is all equal to t to the power of 4. Okay, and now we need to expand and simplify all this. So here we have 2t squared dv over dt, and then we have t cubed d squared v over dt squared, then we have minus 2tv, and then we have minus 2t squared dv over dt, and then we have 2tv plus t cubed v equals t to the 4. And hopefully you can see that this term and this term cancel out, this term and this term cancel out. So we have t cubed d squared v over dt squared, and then we have here t cubed v, and this is equal to t to the power of 4. And if we now divide through by t cubed, you'd find we have d squared v over dt squared plus v equals t, which is equation II. Okay. Now for part B, we have to find the general equation for the displacement of C from O at time t seconds. Now, with this second order differential equation, this non-homogeneous second order differential equation, to solve this and find a general solution, we would first of all have to find the auxiliary equation. So, for part B, the auxiliary equation, you'd find that to be m squared plus 1 equals 0. Of course, you'll notice m is equal to plus minus I. That's quite straightforward. And therefore, our homogeneous solution to this equation, VH, that's equal to a times by the cosine of t plus b times by the sine of t. Now for the particular integral on the right hand side, that's a linear term. So let's just write this down. So for the particular integral, let's try something of the form v equals ct plus d, something of a linear form. And if we differentiate this, dv over dt, you'd find that to equal c, and d squared v over dt squared, you'd find that to equal 0. And now, if we substitute these back into our differential equation here, we can therefore see that this equation therefore becomes the following. We have 0 plus ct plus d equals t. It becomes quite obvious if we compare coefficients. Comparing the t terms, we have ct on the left hand side, t on the right hand side. C is equal to 1 and d comparing the number terms, d is equal to 0. And therefore, our particular integral, vpi, that's equal to t. Okay, so all we've just done over here is substituted c equals 1 and d equals 0 back over here. And therefore, the general solution, VGS, that's equal to a times by the cosine of t plus b times by the sine of t plus t. Okay? And if you remember, the displacement of c from O is given by TV. We were told that in the question. Okay? So let's just write that down. The displacement of c from O is given by x equals TV, and therefore we can see that the general solution is equal to t lots of a times by the cosine of t plus b times by the sine of t plus t. Okay? For part C, for the first part, we have to state what happens to the displacement of c from O as t becomes large, and then comment on the model with reference to this long-term behaviour. Well, what we see over here is that for large t, the displacement gets very large and positive, and then the model suggests the midpoint of the spring moving relative to a fixed point has large displacement when t is large, which is unrealistic, and the spring may reach an elastic limit or will break. That's why it's unrealistic. Question number 4. We have d squared y over dx squared minus 2x lots of dy over dx plus y equals 0, and we have to show that d5y over dx5 is equal to ax lots of d4y over dx4 plus b lots of d3y over dx3, where a and b are integers to be found. So the first thing we can do is, if we take a look at this equation here, let's rearrange to say that d squared y over dx squared is equal to 2x lots of dy over dx minus y. Okay? And with this, what we can now do is differentiate until we get the fifth derivative. And we'd have to use the product rule quite a lot. So the third derivative, d cubed y over dx cubed, differentiating 2x lots of dy over dx using the product rule, we have, if I call this v and this u, we have v, which is dy over dx, times by u dash, which is 2, plus u, which is 2x, times by v dash, which is d squared y over dx squared. Okay, and then we have minus y, so we subtract off dy, the derivative of y, so we have dy over dx. And if we simplify this, we end up with 2x lots of d squared y over dx squared plus dy over dx. Okay, and if we now work out the fourth derivative, d4y over dx4, differentiating this with the product rule, again we have to use vu dash plus uv dash, so we have v d squared y over dx squared times by u dash, which is 2, plus u, which is 2x, times by v dash, so differentiating the second derivative, we end up with the third derivative. Okay? And if we differentiate dy over dx, we end up with d squared y over dx squared. Okay, and what you'd find over here, if we simplify, we end up with 2x lots of d cubed y over dx cubed plus 3 lots of d squared y over dx squared. Okay, so is this right? Yeah. Okay, so if we now work out the fifth derivative, d5y over dx5, if we use the product rule, we have v, which is if we use the product rule, we have v, which is d cubed y over dx cubed times by the derivative of 2x, which is 2, plus 2x lots of the derivative of the third derivative, which is d4y over dx4. And then if we differentiate 3d squared y over dx squared, we end up with 3d cubed y over dx cubed. And if we tidy all this up, we end up with 2x lots of d4y over dx to the 4 plus 5 lots of d cubed y over dx to the 4. Okay, and in conclusion, a is equal to 2, b is equal to 5. That's part A done. Now for part B, hence find a series solution in ascending powers of x as far as determine x to the 5 of the differential equation over here, where y is equal to 0 and x is and dy over dx is equal to 1 at x equals 0. Okay. So if you look in the formula book somewhere, we're finding a series at the point x equals 0, and therefore we'd have to use this Maclaurin series over here. Perhaps if we highlight it, that might make a bit more sense which one I'm on about. We would have to use this, which you should know from your core pure knowledge. So what we need to do is find out the values of all these derivatives at the point x equals 0. And happily for us, they're all related to each other. Now, first things first, we know that y at the point x equals 0 is actually a better way of showing this. We've got y of 0, which is equal to 0. We were told that in the question. And y dash of 0, that's equal to 1. Now, y double dash of 0, we can work this out. If you look at y double dash, we have 2x, so we have 2 times by 0, and then we multiply this by dy over dx at 0, so that is 1, and then we subtract off y, so we subtract off 0. It turns out that the second derivative at x equals 0 is equal to 0. Same thing for the third derivative. If you look at the formula for the third derivative, we have 2x lots of the second derivative plus dy over dx. So we have 2 times by 0, and then we have the second derivative, which we've just found to be 0. Then we subtract off, we add on the first derivative, which is 1. So the third derivative at x equals 0 is equal to 1. The fourth derivative, so 1, 2, 3, 4, at the point x equals 0, that's equal to 2x, so we have 2 times by 0. Lots of the third derivative, so we multiply this by 1, and then we add on 3 lots of the second derivative, So we have 3 times by the second derivative, which is 0. It turns out we get 0. And now for the fifth derivative, so 1, 2, 3, 4, 5, at the point x equals 0, this is equal to 2x times by the fourth derivative. So we have 2 times by 0 plus 5 lots of the third derivative. So we have 5 times by 1. Turns out we get 5. Okay, and now we can use the Maclaurin series. So working this out using the Maclaurin series, which I've highlighted in the formula book here, we have y, which is equal to y of 0 plus x times by y dash of 0 plus x squared over 2 factorial of y double dash of 0 plus x cubed over 3 factorial of y triple dash of 0 plus x to the 4 over 4 factorial lots of the fourth derivative at 0 plus x to the 5 over 5 factorial lots of the fifth derivative, and then we have higher order terms. So we already know all these values, so we have here y of 0, that was 0, and then we have x times by the first derivative at 0, so that would be 1. So we have x times by 1, and then we have x squared over 2 factorial, so we have x squared over 2 times by the second derivative at 0, which was 0, and then we have x cubed over 3 factorial, that was 6, and then we multiply this by the third derivative at 0, which is 1, and then the fourth power of x, we have x to the 4 over 4 factorial, which is 24, and then we multiply this by the fourth derivative at 0, so that would be 0, and then we have x to the 5 over 120, that's 5 factorial, and then we multiply this by the fifth derivative at 0, which is 5, and then we have higher order terms. So in conclusion, if we tidy all this up, we see that y is equal to x plus x cubed over 6 plus x to the 5 over 24, and then we have higher order terms as well. Okay, so that's our final answer. Question number 5. The normal to the parabola y squared equals 4ax at the point P with coordinates ap squared 2ap passes through the parabola again at the point Q with coordinates aq squared 2aq. The line OP is perpendicular to the line OQ, where O is the origin. We have to prove that p squared is equal to 2. So at this point I think it would be a good idea to sketch what's going on. So what I've done over here is I've sketched everything out. We've got our parabola over here, that's y squared equals 4ax. We've got the normal, that's shown in blue over here at the point P, and the normal intersects at another point Q over here. OP is perpendicular to OQ, we see that over here in green. We've got the directrix over here, x equals minus a. We've got the tangent at P, that's shown in this light blue colour all over here. So this is the diagram, and what we need to do is show that p squared is equal to 2. Now what we can do is, if we find out the gradient of the tangent, we can use that to find the gradient of the normal, bearing in mind the tangent and the normal are perpendicular to each other. We can then find the equation of the normal and then use the fact that Q meets the normal to find an equation, and what we can do after that is use the fact that OP is perpendicular to OQ and we'll take it from there. So what we've got to begin with is y squared, which is equal to 4ax, and therefore if we differentiate this using implicit differentiation, on the left hand side we have 2y lots of dy over dx, and this is equal to 4a. And therefore dy over dx, that's equal to 4a over 2y, which is 2a over y. Okay, and if we consider this point P, we can now find out the gradient of the tangent. So at the point P with coordinates ap squared 2ap, if we use these coordinates over here, substituting into this equation for y, we see that dy over dx, that's equal to 2a over y, so we have 2a over 2ap, which is 1 over p. And therefore what we see then is the gradient of the tangent, that's equal to 1 over p, and therefore the gradient of the normal, that's equal to the negative reciprocal of the gradient of the tangent. So we have minus 1 over p, which is minus p. And therefore we can find the equation of the normal. The equation of the normal using y minus y1 equals m lots of x minus x1. We have y minus 2ap equals the gradient minus p lots of x minus ap squared. Okay, and if we start to label these equations, here we have equation 1, here we have equation 2, and here we have equation 3. Okay, so with that, what we can now do is, well, we know that the normal intersects 3 at the point Q. Okay, and Q has coordinates a q squared to aq. And if we substitute this back into this equation, what we have then is y, which is 2aq minus 2ap. This is equal to minus p lots of aq squared minus ap squared. So if we tidy this up a bit, we have 2aq minus 2ap equals minus apq squared plus ap cubed. And therefore we see that we have 2aq plus apq squared equals 2ap plus ap cubed. We'll call this equation 4. Okay, so what we can now do is use the fact that the gradient of OP and OQ are perpendicular to each other. Hence we have the gradient of OP times by the gradient of OQ equaling minus 1. And if we use this information, so we have we have the gradient of OP times by the gradient of OQ equaling minus 1. So if we use this, remember the gradient, that's given by the change in y of the change in x. So if you look at OP, the change in y, that's 2ap, and the change in x, that's equal to ap squared. Remember, we're looking at the gradient of p and the gradient of q. So if we multiply those together, we should end up with minus 1. So we have the change in y of the gradient of OP, that's 2AP over AP squared. And then we multiply this by the gradient of OQ, so change in y over change in x. We have 2AQ over AQ squared, and this is equal to minus 1. So if we simplify over here, we have 4 times by 1 over P times by 1 over Q, so we have 4 over PQ, so let's just write this down. So we have 4 over PQ is equal to minus 1, and therefore Q, that's equal to minus 4 over P. If we call this equation 5, we can now substitute in equation 5 into equation 4 to find out the value of P. Okay, so let's just write that down. If we now substitute in equation 5 into equation 4, we have over here 2a lots of q, so we have 2a lots of minus 4 over p plus apq squared, so we have ap lots of minus 4 over p squared, and this is equal to 2ap plus ap cubed. Okay, and if we multiply through by p and simplify, we'd have to divide through by 2 and the a's cancel. You'd notice that we have p to the 4 plus 2p squared minus 8 equals 0, and if we factorize this, we have p squared minus 2 lots of p squared plus 4 equals 0, so here we have a hidden quadratic, and therefore as p squared plus 4 does not equal 0, it follows that p squared minus 2 equals 0, and therefore p squared is equal to 2. Question number 6. We have a tetrahedron which has vertices A with coordinates 1, 2, 1, B with coordinates 0, 1, 0, C with coordinates 2, 1, 3, and D with coordinates 10, 5, 5. For part A, we have to find a Cartesian equation of the plane ABC. Okay, so first thing we need to do is we need to actually draw out the plane. Okay, and I will do that right now. So having drawn the plane, we've got the coordinates A, B and C, and for us to work out the equation of the plane, we need the normal vector. Now we can get the normal vector by multiplying the vector AB, okay, with the vector AC. Okay, so let's just draw a line here, and if we multiply these two vectors, the result will be a normal vector shown here. So here we have the normal vector. Okay, so multiplying those vectors together, the normal vector is equal to AB multiplied by AC. And if we work this out, we have AB, so we have minus 1, minus 1, minus 1, multiplied by AC. AC, that would be 1, minus 1, 2. And if we multiply these vectors together, let's use our calculator, so let's go to the vector mode. Define vector A with components minus 1, minus 1, minus 1. Let's now define vector B with components 1, minus 1 and 2. And when we come to multiply these together, it turns out we get -3, 1 and 2. Okay, so that's our answer for the normal vector. Now, the equation of a plane that's given as r dot product with n equals some general vector a dot product with n. Okay, now a can either be a, b or c, it doesn't make a difference. I will choose b because that has zeros in it and that will make my calculation a lot easier. So we have the vector r, that would be x, y, z. We dot product this with our normal vector -3, 1, 2, and this is equal to some general point on the plane 0, 1, 0, that's b, and we dot product this with the normal vector -3, 1, 2. And if we work this out, you'd therefore find we have -3x plus y plus 2z on the left hand side, and on the right hand side we have just 1. Okay, so that's part A done. Now for part B, we have to find the volume of the tetrahedron. Okay, so first things first, let's actually draw out the tetrahedron. So having drawn the vector as the tetrahedron, the volume of the tetrahedron, okay, that's equal to 1/6 lots of the magnitude of AD dot product with AB times by AC. And we've already worked out what AB times AC is. We have found that to be -3, 1, 2. Okay, maybe if we highlight that. So this over here, we've worked out to be this over here. So we now need to work out AD. So AD, that would be starting at A, finishing at D, that would be 9, 3, 4. So in terms of the volume then, we'd have 1/6 multiplied by the magnitude of AD, which is 9, 3, 4, dot product with this thing over here, -3, 1, 2. Okay, so working this out, we have 1/6 lots of the magnitude of, well, here we have -27 plus 3, which is -24, plus 8, which is -16, and then divide that by 6, we get a value of 8/3. So therefore the volume is 8/3 units cubed. Okay, so now for part C, the plane pi has equation 2x minus 3y plus 3 equals 0, and the point E lies on AC and the point F lies on the line AD. Given that pi, this plane over here, contains the point B, the point E and the point F, we have to find the value of k such that AE is equal to k lots of AC. Okay. So what we have over here then for part C is, well, given already, we know that AE, let's write this out neatly, AE is equal to k lots of AC. Okay, now we can actually work out what AE is by multiplying AC by k, and we already worked out what AC was. AC, which is this vector over here, we have AC, which was what we've worked out before. So we have k lots of 1 minus 1, 2, which if we work this out, it turns out we get k minus k and 2k. Okay, now that's what AE is, and AE, that's defined as OE minus OA in relative vector form. So therefore we can see that OE, that's equal to AE plus OA. Now the reason I want to work out OE, if I know the coordinates of E, I can substitute that back into, well, the coordinates of E first of all, that will be in terms of k from here, and what we can then do is substitute that back into this equation of the plane to figure out the value of k. So if we actually work out what E is, OE, that's equal to AE, which we just said was k minus k and 2k, plus OA, that would be 1, 2, 1. Okay, so all I've just done over here is use this coordinate here, and if we work out this result, you can therefore see that OE, that's equal to 1 plus k, 2 minus k, and 1 plus 2k. Okay, and therefore the coordinates of E are 1 plus k, 2 minus k, and 1 plus 2k. Okay, now we know that E lies on the plane, so let's write that down. E lies on the plane, so let's just give ourselves a bit more room. Let's insert a new page. So if E lies on the plane, we have over here 2 lots of x, so x over here is, well, the x coordinate of E, that's 1 plus k, and then we have minus 3 lots of y, so we have minus 3 lots of 2 minus k, and then we add on 3, and this is equal to 0. And if we work out what k is, well, we have 2 plus 2k minus 6 plus 3k plus 3 equals 0. You can therefore see k is equal to 1/5. Okay? And then for part D, given that AF is equal to 1/9 of AD, we have to show that the volume of the tetrahedron ABCD is 45 times the volume of the tetrahedron ABEF. Okay, so what does this mean? Well, let's actually draw out that plane. So I've drawn out the tetrahedron, I meant to say. I've drawn out the tetrahedron ABEF. Now, it's important that you get this diagram right, because what we know already is E, okay, lies on the line AC. So if we sort of extend this, here we have the point C. Okay, so E lies on that plane over here, and then we've got this F over here. So that's quite important. You get this the right way around. So therefore the volume of ABEF, that's equal to 1/6 lots of the magnitude of AF, okay, so that's the normal one to the plane, dot product with AB times by AE. Okay, now AF, if you go back to the question, we were told AF that's equal to 1/9 of AD. So AF that's equal to 1/9 of AD. Okay, and then we dot product this with AB times by AE. So we have AB times by AE, and AE, if you go back to the question as well, we were told AE is equal to KAC, and K, we were, this K over here, we found K to be this 1/5 over here. And therefore, we have over here AB multiplied by 1/5 AC. Okay? And if we take out all these constant numbers, we have 1/6, lots of 1/9, lots of 1/5, lots of the magnitude of AD, dot product with the product of AB times by AC. Sorry, here, I don't know what I was saying D for. This is supposed to be F. No, sorry, this is D. This is D, sorry. Okay, because AF is equal to 1/9 AD. And if you compare this bit before, well, here AD dot product with the AB times AC, that's what we had for this volume over here. So this was the volume of the tetrahedron ABCD. So if we rewrite this, we have the 1/9 times by the 1/5, that's 1/45. And then we multiply this by 1/6 lots of AD dot product with AB times by AC. And hopefully you can see that this bit over here, this is the volume of ABCD. Okay, so the volume of ABEF is 1/45 lots of the volume of ABCD, and that's what we needed to show. Okay. Question number 7. We have P and Q, which are two distinct points on the ellipse described by the equation x squared plus 4y squared equals 4. The line L passes through the point P and the point Q. The tangent to the ellipse at P and the tangent to the ellipse at Q intersects at the point RS. We have to show that an equation of the line L is 4sy plus rx equals 4. I think at this point it would be a good idea to sketch this problem out. So what I've done over here then is I've just sketched out the problem. We've got our ellipse that's shown in red. We've got x squared plus 4y squared equals 4. So it intersects over here at 1 and minus 1 and at minus 2, 2. And then we've got this line L which passes through, sorry, we've got P and Q which are distinct points on the ellipse, okay? So that's quite important. P and Q are two distinct points on the ellipse. And then we've also got this line L which passes through P and Q. So what I've done over here then is I've shown that we've got this point P and this point Q, and the line L passes through P and Q, that's shown in the light colour blue, and then we've got the tangent to the ellipse at P, that's shown in this darker blue, and the tangent to the ellipse at Q, that's shown in green over here. They intersect at this point RS, which is shown in orange. We have to show that the equation of the line L is this. Okay, so hopefully sketching the problem out might make this problem a tiny bit easier. Okay, so first of all, we've got x squared plus 4y squared equals 4. We'll call this equation 1. Now, because we're talking about tangents, it would be a good idea to work out the dy over dx, so we can actually find out what the tangent is at the point P and at the point Q. And notice I don't know the exact values of the coordinates of P and Q. It could be anywhere on the ellipse. So for example, P could instead be over here and Q could be over here. Well, Q could be over here somewhere. It doesn't matter where it is. This is just a quick sketch, and I don't know, because I don't know the coordinates of P and Q, I've just given them arbitrary constants x1 and y1 for P, x2 and y2 for Q. So I've got this first equation here, and if I differentiate using implicit differentiation, we end up with 2x plus 8y dy over dx equals 0. Now that's quite useful because we can therefore see that dy over dx, that's equal to minus x over 4y. Okay? Now, we can now find out the equation of the tangent at P and the equation of the tangent at Q, okay, by substituting in these coordinates into this function here. So, at the point P, with coordinates x1, y1, we have the gradient of the tangent, which is equal to minus x, so we have minus x1 over 4y, so we divide this by 4y1. And using y minus y1 equals m lots of x minus x1, hopefully you can see that we have y minus y1 equals minus x1 over 4y1 lots of x minus x1. Okay, and if we tidy this up, we have 4y1 minus y1 squared equals x1 squared minus xx1. Okay, and if we rearrange this, we have x lots of x1 plus 4y1 equals x1 squared plus 4y1 squared. We'll call this equation 2. And we also know that P lies on the ellipse. So therefore, if P lies on the ellipse, then if we substitute this coordinate P back into the equation for the ellipse, we have over here x1 squared plus 4y1 squared equals 4. We'll call this equation 3. So this equation comes from the fact that that P is a distinct point on the ellipse. And we can do the same thing with Q. Q has coordinates x2, y2, and if we substitute in, we arrive at the exact same thing as we did over here. So the gradient of the tangent, that's equal to minus x2 over 4y2. So using y minus y1, well, in this case it'll be, if you think about it, it'll be y minus y2 equals the gradient minus x2 over 4y2 lots of x minus x2. Okay, and if we tidy this up, obviously we'll end up with a similar thing to what we did in equation 2. We'd have x2 plus 4y2. Let's expand and simplify first. So we have I'll write it out in full. So we have 4y2 minus 4y2 squared equals x2 squared minus x2, and if we rearrange this, we end up with a similar thing in what we have in equation 2. We have x2 plus 4y2 equals x2 squared plus 4y2 squared. Okay, so we'll call this equation number 4. And also, using the fact that Q lies on the ellipse, so we were told Q lies on the ellipse, we can also conclude that we have x2 squared plus 4y2 squared equals 4. So all I've done over here is, again, I've substituted the coordinates of Q back into equation 1. So this over here is equation 5. Okay, now what do you notice? Hopefully you'll notice that this bit over here is the same as this bit over here. So we have, on the right hand side of equation 2, x1 squared plus 4y1 squared matches up with this one, and same thing over here. This bit matches up with what we have over here. And hopefully therefore you can see that because of this, because equation 3, because the right hand side of equation 2 is equal to the left hand side of equation 3, and similarly the right hand side of equation 4 is equal to the left hand side of equation 5. Hopefully you can see that we have two further equations which we can write. We have x lots of x1 plus 4y lots of y1 equals 4. Okay, we'll call this equation 6. And we also have x lots of x2 plus 4 lots of y2 equals 4. We'll call this equation 7. So what we have over here then are the equations of the tangents. Okay, so hopefully that makes sense what we've just found out then. So here we have the equation of the tangent at the ellipse at P. That's equation 6. So let's just underline this. And then we also have in the green colour the equation of the tangent at Q. So hopefully all that makes complete sense. And what we already know is that this equation 6 and 7, they intersect at the point R. They intersect at the point RS. So let's write that down in orange. Equation 6 and equation 7 intersect at the point RS. Now, this is important because RS, we substitute into 6 and 7, what you'll end up with is R lots of x1 plus 4s y1 equals 4. So that's equation 8. Okay. And R lots of x2 plus 4s y2, that's equal to 4. Call this equation 9. And the reason we've got these equations 8 and 9, we can now use this information to find out the gradient. And the gradient of this blue line over here, that's equal to the change in y over the change in x. And we can relate that to what we have over here in terms of R and S. And the reason I want to do that is because if I know the gradient, I already know these coordinates over here, we can find the equation of L. Okay? So, having said that, what we can now do is find the gradient of L. So let's write that down. Now find the gradient of L. So the gradient is equal to the change in y over the change in x. So we have the gradient y2 minus y1 over x2 minus x1. Hopefully that makes complete sense over here. The gradient of this blue line, this light blue line, that's equal to the change in y, y2 minus y1 over the change in x, x2 minus x1. Now, hopefully you can recognise that if we subtract equation 9 from equation 8, we can actually find out what y2 minus y1 is over x2 minus x1 is in terms of R and S. So let's do that. If we subtract 9 from equation 8, sorry, if we subtract equation 8 from equation 9, well, let's do that. We have rx2 minus rx1, so we have rx2 minus rx1, and then we have 4sy2 minus 4y(s1), so we have 4sy2 minus 4sy1, and this is equal to 4 take away 4, which is 0. So let's factorize. We have r lots of x2 minus x1 plus 4s lots of y2 minus y1, and hopefully from here we can rearrange to get y2 over y1. We can find out a value for this. So if I call this equation 10, we know that this is equal to 0. So we have 4s lots of y2 minus y1 equals minus r lots of x2 minus x1. And then hopefully you can recognize that in conclusion, y2 minus y1 over x2 minus x1, that's equal to minus r over 4s. Okay, we'll call this equation 11. So knowing that, we can now find the equation of L. So finding the equation of L, we have y take y1, okay, equals minus r over 4s lots of x minus x1. So all I've done over here is I know the gradient of this line L, okay, and we can therefore use you can either use the coordinates of Q or the coordinates of 1. Doesn't make a difference. I will use the coordinates of P. So we have this for our equation for L1. And if we tidy this up a bit, we have 4sy minus 4sy1. This is equal to minus rx plus rx1. Okay, so let's tidy this up a bit more. So let's just give it a chance to load. Let's insert a new page. So continuing on from here, we have 4sy plus rx equals 4sy1 plus rx1. Okay, so hopefully that makes sense. So we'll call this equation 12. And if you notice, this bit over here, this right hand side of this bit is equal to the left hand side of what we had in equation 8. So we can equate them. So instead of having 4sy1 plus rx1, we can replace this with 4. So if we do that, so if we now substitute in equation 8 into equation 12, hopefully you can see that therefore, in conclusion, 4sy plus rx is equal to 4. Call this equation 13. And that's exactly what we wanted to show over here. Bit of a complicated question, but hopefully you can see everything fit nicely together. Question number 8. We have figure 1 over here, which shows the graph of the function h of x with equation h of x equals 45 plus 15 sine x plus 21 sine of x upon 2 plus 25 cos of x upon 2, where x belongs to a set of numbers between 0 and 40. For part A, we have to show that dh over dx is equal to t squared minus 16 minus 17 lots of 9t squared plus 4t minus 3 all over 2 lots of 1 plus t squared squared, where t is equal to tan of x upon 4. So with our with our t formula, what we can do over here, I'll just write it out in rough. If we had, say, well, over here we've got x upon 2 and here we've got x upon 4. Now let's suppose we had here theta, okay, and let's suppose here we had theta upon 2, then it would be fine for us to make those relevant substitutions in terms of t. Now because we've halved everywhere, we can still make those substitutions, so it's perfectly legitimate for us to still use the t formula in this question. Okay, so don't be put off by that. We can still use the regular t formula because we've just halved everything inside the bracket. Okay, so having said that, for part A, we begin with h of x equaling 45 plus 15 sine x plus 21 sine of x upon 2 plus 25 cos of x upon 2. And now we can find out what dh over dx is, because that's what we need to find in the question. So dh over dx, well, differentiating 45, that'll disappear, and differentiating 15 sine x, that would be 15 cos x. We'll just put this in a bracket. And then differentiating 21 sine of x upon 2, we end up with 21 over 2 lots of cos of x upon 2. And then differentiating 25 cos of x upon 2, we end up with 25 over 2 sine of x upon 2. And we'd have to use the double angle formula over here. The reason being, well, I'll show you why. Because here we want to put everything in terms of t, and it'll be perfectly fine for us to use the t formula when we have t equals tan of x upon 4 for this term and this term, but this term gives us a bit of problems. So instead we have to use a double angle formula to rewrite cos x. And we can do that in the following way. So first of all, you'll have to notice that actually, let's just write down note. Cos of 2a, that's equal to 2 cos squared a minus 1, which if we rewrite, hopefully you can see that therefore cos of x is equal to 2 times by the cosine of x upon 2 x upon 2 squared minus 1, and therefore we can make this relevant substitution here. So we can replace cos x with 2 cos of x upon 2 squared minus 1. So we have dh over dx, that's equal to 15 lots of this thing over here. So we have 15 lots of 2 times by the cosine of x upon 2 squared minus 1. And then we have the rest of the terms over here, 21 over 2 cos of x upon 2 plus 25 over 2 sine of x upon 2. And we can now use our substitution of t equaling x upon 4. So we can hopefully see that dh over dx, this is equal to 15 lots of, well, if I write this in a big bracket, we have 15 lots of 2 times by, well, cos of x upon 2 in terms of t, we have 1 minus t squared over 1 plus t squared. Okay, and then we minus 1. So that's that term. And then we have 21 over 2 lots of cos of x upon 2, so we have 1 minus t squared over 1 plus t squared, and then we have minus let's double check this. Oh, sorry. This is minus. Differentiating cos gives minus sign. So yeah, just be a bit careful over here. So we have minus 25 over 2 times by 2t over 1 plus t squared. Okay, now if you take a look in the question, on the denominator over here, we have 2 lots of 1 plus t squared squared. Sorry, here we should have squared because we have cos squared, okay? So maybe if I highlight that, just don't forget that. Right, I think at this point it would be a good idea just to expand everything out and simplify. So here we have 15 times by 2, which is 30. So we have 30 lots of, well, this term I'm going to write as 1 plus t squared squared over, sorry, 1 minus t squared squared over 1 plus t squared squared. And then we've got 15 times by minus 1, which is minus 15. Then here we have 21 over 2 lots of 1 minus, let's write this out neatly, 1 minus t squared over 1 plus t squared. And here we have minus 25 over 2 lots of 2t over 1 plus t squared. Now, sorry, 1 plus t squared, like that. Now, like I said before, the denominator over here is 2 lots of 1 plus t squared squared. So we want to rewrite every single term over here in terms of that common denominator. So for this first term over here, we would have 60 lots of 1 minus t squared squared over 2 lots of 1 plus t squared squared. Hopefully you can see they're exactly the same. It's just that 60 over 2 is the same as 30. Now this minus 15, that's the same as minus 15 lots of, well, because we want to write it over a common denominator of 2, here we have 30 over 2 lots of 1 plus t squared squared, and on the bottom here we have the 2 lots of 1 plus t squared squared. Okay, so that's this 15 done. Remember, 15 is the same as 30 over 2, and here the 1 plus t squared squared over 1 plus t squared squared cancels out. Now this term over here, we would have to multiply this by the 21 lots of 1 minus t squared, we'd have to multiply by 1 plus t squared, and then on the bottom we've got this 2, we've got this 1 plus t squared squared, and hopefully here, well, 21 over 2, that's fine. Then the 1 minus t squared over 1 plus t squared, hopefully here you can see that the 1 plus t squared cancels once with the 1 plus t squared squared to give this term here. And finally with this thing, exactly the same thing, we have minus 25 lots of 2t lots of 1 plus t squared, and on the bottom we've got 2 lots of 1 plus t squared squared, and hopefully you can see 1 plus t squared over 1 plus t squared squared cancels out to give this term here. So these are equivalent. So that's a bit, it's quite a lot to get your head round in my opinion, if you can get that far. But after that, we simply have to combine everything on the top. So we have 60 lots of 1 minus t squared squared, minus 30 lots of 1 plus t squared squared, plus 21 lots of 1 minus t squared lots of 1 plus t squared, minus 25 lots of 2t lots of 1 plus t squared. Okay, so let's get a ruler and rule this off. And on the bottom we have 2 lots of 1 plus t squared squared. So next step would be to simply expand all this on the top and simplify. So we have 60 lots of, well here, 1 minus t squared all squared, that would be t to the 4 minus 2t squared plus 1. And then here we have minus 30 lots of minus 30 lots of t to the 4 plus 2t squared plus 1. And then here we have 21 lots of a difference of 2 squares, so here we have 1 minus t to the 4. And then here we have, if we tidy all this up, we have 50 t minus 50 t cubed. Okay, so that's that term done. Let's rule off. And then on the bottom we've got 2 lots of 1 plus t squared squared. Okay, now let's expand even further. So we've got here 60 t to the 4 minus 120 t squared plus 60 minus 30 t to the 4 minus 60 t squared minus 30 plus 21 minus 21t to the 4 minus 50t minus 50t cubed. Alright, and then on the bottom over here we end up with 2 lots of 1 plus t squared squared. Okay, so if we tidy all this up, you'd find if we take all the terms in terms of t to the 4, we'll end up with 9t4, and then if we simplify the rest we have minus 50t cubed minus 180 t squared minus 50t plus 51, and then we divide this entire thing by 2 lots of 1 plus t squared squared. Now if you compare this with what we have over here, well here we have 9t squared times by t squared, that would be 9t to the 4. The minus 17 times by the minus 3, that gives the positive 51. In terms of the t cubes, well we have 4t, well here we have 4t cubed minus 9 times by 6 times by t cubed, that gives the minus 50. And then in terms of the t squares, well we have t squared times by minus 3 minus 17 times by 9 times by t squared, and then we've got minus 6t times by plus 4t, so that gives the minus 180 t squared. And then in terms of the t's, we've got here minus 6 times by the minus 3 and the minus 17 times by the 4, and then the numbers we've discussed. So yeah, those are the same things. So indeed we do get t squared minus 6t minus 17 lots of 9t squared plus 4t minus 3. On the bottom we end up with 2 lots of 1 plus t squared squared. Okay, now for part B of the question, we've got figure 2 over here, which shows a graph of predicted tide heights in meters for Portland Harbour from 8 o'clock on the 3rd of January 2017 to the end of the 4th of January 2017, and the data is taken from here. The graph of k lots of h of x, where k is a constant and x is the number of hours after 8 o'clock in the morning on the 3rd of January, can be used to model the predicted tide heights in meters for this period of time. For the first part of part B, we have to suggest a value of k that could be used for the graph of k of h of x to form a suitable model. Well, if you look over here, between figure 1 and figure 2, they're exactly the same graph. The only difference is here, these values over here on the vertical axis are a bit different. And what we can do is, to find the value of k, we can compare the values. So here we've got a value of 70, and here we've got a value of 1.6 at this point where it intersects the vertical axis. So we can compare those values by dividing them by each other to see how many times smaller this figure 2 is than figure 1. So we've got over here, for the first part of part B, we've got the 1.6 over the 175. And if we work this out, 1.6 divided by 175, that would be 8 over 875, which is the same as sorry, what have I done here? Sorry, we have 1.6 over 70, so 1.6 divided by 70, that would be 4 over 175. So sorry, I was just working ahead. Which as a decimal is the same as 0.0228, etc. So therefore k can take this value of 4 over 175. Okay, so that's the first part. And now for the second part. Why may such a model be suitable to predict the times when the tide heights are at their peaks, but not to predict the heights of these peaks? Well, we have the following reason. So it's suitable for time since the graphs both oscillate bimodally with about the same frequency. So what that means is if you compare the x-axis here with the time axis here, they're about the same. Okay, so the frequency is about the same, so that's between one peak and another peak. But in terms of the vertical axis, well, h of x has a fixed peak, and we can see that over here, whereas this graph over here does not always have a fixed peak because it's a tide and tides go up and down and they're not always constant at the peak, okay? And that's what we've put over here. It's suitable for time since the graphs both oscillate bimodally with about the same frequency, and it's not suitable to predict the height since the height of the peaks vary over time, but the graph of h of x has a fixed peak. Okay. Now for part C, we have to use figure 2 and the result of part A to estimate to the nearest minute the time of the highest tide height on the 4th of January 2017. So we're looking in this region over here. Okay, so to do that, because we're looking at the highest tide height, we want this to be a maximum, and therefore, so we want a maximum, and therefore we'd have to find dx of dh, which we've already done, and set it equal to 0 because we're concerned with a maximum. Alright, so let's quickly do that. So what we need to do is copy this and set it equal to 0. So we've got this equation over here, which was dx over dh, and we set that equal to 0. And if we do that, obviously we'll end up with t squared minus 6t minus 17, lots of 9t squared plus 4t minus 3 equals 0. And if we solve for the values of t, so let's grab our calculator. So let's just quickly do this on the equation solver. Here we have t squared minus 6t minus 17. That would be 3 plus minus root 26. And for the next one, we have 9t squared plus 4t minus 3. So we get minus 2 plus minus root 31 over 9. Okay, so that's that bit done. So now we'd have to use this one over here. Now you have to be a bit careful over here. If we actually work out what, so if I go back here, you'd see this value is 0. If you look at this quadratic, maybe if I write out the solutions here, we have t equals, what do we have t equaling? We have t equaling 0.396, etc. and also minus 0.840, etc. Okay, and if we take a look over here of what the numerical values of t are, well, we have t squared minus 6t minus 17. We end up with a value of t equaling 8.099, etc., and also minus 2.099, etc. And essentially, what you need to bear in mind is the max peak height occurs at the smallest, if you go back here, the max peak height, okay, would occur at the smallest value of x, and you can see that over here. It's just that we're just going to be adding multiples of pi to find the third peak, which corresponds to the 4th of January. So we want the smallest value of x first, okay, and once we've found this smallest value of x, we want the third peak after that, which will correspond to the 4th of January. So to get the smallest value, okay, we'd have to use these solutions over here instead of this solution over here. Hopefully that makes sense what I'm talking about. Okay, so we want the smallest the smallest value of x, okay? And when I said smallest value of x, I mean the smallest positive value of x. So let's write that down. Let's write it down in this color. The max peak height occurs at the smallest positive value of x. Okay, and you can see that over here. So if you go back over here, the smallest value of x gives this max peak, okay, and we're finding out what this value of x is, okay, and then we will translate that into some sort of a time. So the way we can do that is the following. Well, we have t equals tan of x upon 4, so we have tan of x upon 4, that will equal, and if you actually take a look at the different values you get, make sure you're in radians, so the inverse tan of minus 0.840, etc. And then we have to, sorry, I'm just thinking over here, and then we have to add pi to it. Okay, so we'll take it, let's consider this minus 0.840, etc. So inverse tanning both sides, x over 4, that's equal to, well, if I go back here, well, we have the inverse tan of minus 2, let's put this on fractions, we have minus 2 minus root 31 over 9, which is 0.3, sorry, make sure that your minus is in the right place. So we have x upon 4, which is equal to minus 0.699, etc. And for the, well, then we can find out x from here. So if I multiply this by 4, we come out with a value of minus 2.796, etc. So let's now find the next value. So if I divide this by 4, and let's add on pi. So adding on pi, we come out with a value of 2.442, etc. And then if we what do we do? If we I'm trying to think. If we times this by 4, we get a value of 9.769, etc. And then what else can we do? Well, if we consider this inverse tan of minus 2 plus root 31 over 9, we get a value of 0.377, etc. And then if I times this by 4, we get a value of 1.509, etc. So we'd have to use both these solutions, 0.396 as well. Okay, and the reason we use this one again is because this one will give much bigger values, so that's quite important. And obviously we want the smallest positive. The smallest positive, you'd find that to be the 1.509, etc. Okay, so the next thing to notice is that we want the third peak. So we want the third peak, which corresponds to the 4th of January. Now, if you look at the third peak, so let's go back to the diagram. If you look at the third peak over here, this corresponds to the maximum tide height. Let's actually go back to the question. This gives the maximum tide height on the 4th of January, and you can probably see that over here. It corresponds quite well. So we want a value of x around 25. So, well, we've got this 1.509, etc. Let's keep adding on pi until we get a value of around here. So if I add on pi, still too small. Add on another pi, still too small. Add on another pi, still too small. Add on another pi, it's still too small. Add on another pi, it's still too small. Add on another pi, it's still too small. And if we continue, we've added 8 lots of pi to get this value of 26, which is around over here, isn't it? It makes complete sense. So therefore, you'd hopefully see that t is equal to this 1.509, etc. plus 8 pi. Now I've added 8 pi to get a value that's in this region of the third peak, okay? So remember, it's finding the maximum, the minimum, the maximum, and then this one, then this one, and this one, this one, and this one, and then this one. So we've added 8 pi because of that reason. So let's just count that. So we've got 1, 2, 3, 4, 5, 6, 7, 8. So the reason we had to add on 8 pi was to get that third peak, we needed to add on 8 pi. Okay, so we've had 1, 2, 3, 4, 5, 6, 7, 8 over here. So hopefully that makes a bit of sense. So that's why we've added the 8 pi, and it turns out we got a value of 26.642, etc. So what does this mean? Well, this is the same as 26 hours, and then this times this by 60, and then we have 26 hours and 39 minutes. It's 29 hours 36 minutes after 8 AM on the 3rd of January. Okay, so therefore the time t let's just write this down. We see that the time of the greatest tide height is approximately 10:39 AM. So that over here is our final answer, 10:39, okay? So that's the end of this paper.